We can also determine differentiability if we just have an equation, just like we were doing for continuity. How that works is that for f of x to be differentiable at x equals c, f of x must be continuous and the derivative as we approach from the left must be the same as the derivative as we approach from the right. So our first step, what we're looking for is is f of x continuous? So that means the limit as x approaches c from the left equals the limit as x approaches c from the right equals f of c. Secondly, is the derivative the same as we approach from the left and the right? So what that means is the limit as x approaches c from the left of f prime of x. Notice this prime right there, and that should be equal to the limit as x approaches c from the right of f prime of x. So what we did to check with continuity, we're just doing the same thing with f prime. So let's look at a few examples. F of x equals x squared if x is less than 3, and x squared minus 5 if x is greater than or equal to 3. So first thing we're looking at is f of x continuous. So the limit as x approaches 3 from the left. So on the left-hand side, that's x squared. That's 9. The limit as x approaches 3 from the right. So the right side, that's x squared minus 5. So 3 squared minus 5, or 4. Those limits don't match. So not continuous. Therefore, not differentiable. For our second problem, let's say g of x is x plus 6 if x is less than or equal to -1, and x squared plus 4 if x is greater than negative 1 is g of x differentiable? First, let's check, is it continuous? X approaches negative 1 from the left function is x plus 6, so it's negative 1 plus 6 equals 5. From the right, that's x squared plus 4, so that's negative 1 squared plus 4, that also equals 5. So those match. And then g of negative 1. Okay, so here's the equals to sign, so that's negative 1 plus 6 equals 5. Those all match. Yes, it's continuous. But we can't stop there. For it to be differentiable, it has to both be continuous and the limit of the derivative. This should be as g of x differentiable at x equals negative 1, because that's the only point of interest. We can see that it's differentiable or continuous for the rest. So as x approaches negative 1 from the left, let's see what we've got. So first of all, g prime of x, I'm just going to take the derivative of each of these. That's 1 if x is less than or equal to negative 1. It's 2x, bring down the exponent, if x is greater than negative 1. So this is going to be the limit as x approaches negative 1 from the left of 1. There's nowhere to put in x, so the answer is just 1. Whereas the limit as x approaches negative 1 from the right of g prime of x, the function on the right is 2x. When we plug that in, 2 times negative 1 equals negative 2. Because 1 does not equal 2, the function is not differentiable. Okay, let's do our third problem, just asking after differentiability. Is h of x differentiable at x equals 1? That's our question. Okay, so first we're going to check on continuity. And when x is less than 1, the function on the left is negative x squared plus 2. When we're approaching from the right, our function is negative 2x plus 3. And h of 1 is this one, negative 2 times 1 plus 3. So yes, it's continuous. So far, so good. Now we have to check with the derivative. So the derivative here is negative 2x if x is less than 1, negative 2 if x is greater than or equal to 1. And so let's check the limit as h prime of x as x approaches 1 from the left. So we can see that we're going to use the left one. Substitute in negative 2 times 1 equals negative 2. And then the limit as x approaches 1 from the right of h prime of x is going to be the limit as x approaches 1 from the right of negative 2. That's just negative 2. Notice how these two match. So that means that yes, h of x is differentiable right and left limit of h prime of x at x equals 1 are the same. Our final type of problem are mixed problems. An important thing to realize is just what knowing one of these pieces in terms of whether f of x has a limit, is differentiable, or is continuous, what does that tell us about the other ones? So let's start off. If f of x is differentiable at c, which of the following must be true? Okay, well, we know when we were doing the other problems that in order to tell if something was differentiable, we first had to know that it was continuous. So in order for it to be differentiable, it must also be continuous. Because if it's not continuous, it can't be differentiable. But it is differentiable, so it must be continuous. The limit as x approaches c of f of x exists. That means the left-hand limit and the right-hand limit are the same. That's part of our test for being continuous, so that must be true as well. If these aren't the same, if the left and the right-hand limit are not the same, then function can't be continuous, then the function can't be differentiable. However, if f of x is continuous at c, which is true, f of x is differentiable at c, limit as x approaches c of f of x exists. Well, just because a function is continuous doesn't mean it has to be differentiable. If we went back to our little graph earlier, right here at this point, f of x is continuous. We don't have to lift our pen, but there's a sharp turn, so it's not differentiable. However, just like we said up here, this limit has to exist in order for the function to be continuous. If the function is continuous, then this limit must exist. So let's do that third one. If the limit as x approaches c of f of x exists, which is true? Actually, I should probably say which must be. Because it could be differentiable, it just doesn't have to be. F of x is continuous at c, f of x is differentiable. Well, looking back at that graph again, if we look here at this removable discontinuity, the limit from the left and the limit from the right are the same. The limit does exist, but the curve is not continuous, and so the curve is not differentiable either. So for this one, neither of these have to be. So it's basically a chain. If we know the limit doesn't exist, it's not continuous, it's not differentiable. If we know that it's continuous, then the limit must exist, but it doesn't have to be differentiable. If it's differentiable, then the other two have to be true as well, because they're prerequisites. Okay, let's look at two other types of problems. Which of the following must be true? Actually, this one can just be is, because we just have one function. F of x has a limit at x equals 2. F of x is continuous at x equals 2, and f of x is differentiable. At x equals 2. So let's start off with that limit. It has an overall limit if, I'm going to number these, let's do 1, 2, and then 3. So to find out this first one, overall limit just means that they've got the left limit and the right limit. So let's go ahead and find that. The left-hand equation is 3x squared. So that's 3 times 2 squared, or 12. And then the limit as x approaches 2 from the right. The right-hand function is x plus 10. So if we plug in 2, that's 2 plus 10 equals 12. So that means this one's yes. Is it continuous? That means, does this overall limit equal g of 2? Well, let's see. G of 2, it's equal to 2 right here, so that means we're using x plus 10, so 2 plus 10 equals 12. So yes, because this is the same as the limit that we found up here. And then finally, is f of x differentiable? So that means that the limit as x approaches 2 from the left of g prime of x equals the limit as x approaches 2 from the right of g prime of x. So g prime of x, if we take the derivative of 3x squared, that's 6x. Right there. If x is less than 2, the derivative here is going to be 1. Okay. The left function is 6x. Plug in the 2, that's 12. Limit as x approaches 2 from the right. The right-hand function is 1. It's always 1. These ones don't match. So that means if we come back up here, differentiable, no, just the first two are true.